a fourth assignment?
Yes, I'm going to upload it. Okay, and I'm going to talk to you about it for assignment. Okay, so don't panic, relax. Okay, right. So today the agenda is we are going to talk about the effects of strain hardening, strain rate, and thermal softening on metal cutting process parameter. So we're going to look at, okay, so if we have a certain type of material, okay, how are we going to have a very intelligent guess on what process parameter to use? Okay, very intelligent. Last week we talked about rake angle, yes or no? So we talk when you have high A value, you use negative rake. When you have low A value, you can use positive rake or negative rake. You'll be fine. But I also tell you the consequences, yes or no? Right. So this week we're going to talk about the effect of strain hardening, okay, and strain rate and thermal softening on metal cutting process parameter. Then after that, we're going to talk about the mechanics of metal cutting. Okay, we're going to draw some vectors. Okay, very simple vectors, high school physics vectors. Okay, no rocket science stuff. And then we're going to shear angle predictive model. Okay, we are going to try to see one predictive model. So as I explained how I wish I'm teaching you face to face, we will have another week. Okay, because online usually is slower. So the face-to-face, I will teach you how to do temperature calculation. Okay, but I don't have enough time for that, unfortunately. Right. Anyone, any questions so far? Nope. So we are going to look at B and N values in the strain hardening. Okay. Okay. In the strain hardening on a process parameter. Okay. So the B and N, as I think I did write this out before last week. Okay, which I'm going to repeat again. The B and N values, okay, will determine the minimum magnitude of undeformed chip thickness. Okay, and selection of cutter path. Okay, I will talk about cutter path later, so don't panic yet. Okay, we'll talk about cutter path. Okay, so let's look at B and N. Okay, so we were to recall what does the effect of B and N. So we are going back to our fundamentals again. We draw stress strain curve. Okay, we go back to our stress strain curve. So this is strain, this is stress, and we know based on Johnson-Cook equation, over here this is our A, right? And then we have one curve, and then we have the other curve. Okay, so this curve will have B1, N1, and the steeper one is B2 and N2. Right? Because of the expression of the equation, I cannot decouple them. So the equation that we are looking at for now is plastic stress is equal to A plus by B epsilon PLN, power of N. So that is the equation we're looking for. So for this case, we know that B1 is less than B2 and N1 is less than N2. Okay. So if you have two materials with the same A values for this case, how will you select your process parameter? Okay. So I'm going to write I'm going to draw a table. So the table. So this is our B and N combination. So we have low and we have high. Right. And for example, if our undeformed chip thickness is the next one, undeformed chip thickness. Okay, I will write for one first. Okay, for the low, we can take 0.001 0.05 millimeters. Okay. And then the next column, we have cutter path. Planning. So do you all want to can someone make a guess? If the material with low B and N, your undeformed chip thickness is 0.05 millimeters. So for low means it's this one, right? If you have high B and N, right? Can anyone make a guess and tell me why? Is it lower or higher, please? Anyone, please. Is it going to be lower or is it going to be higher? Come on. Hello. Higher. Why?
Because of the angle. Is it the positive angle?
No, your answer is not right. Your answer is right, but the reason is wrong. Okay? Can anyone?
The larger angle, no?
Huh?
It's gonna be a lot longer because of the larger angle.
No, not the right. You guess the right. You go higher, but that's not the reason. Okay? So in general, when you go to industry, okay, when you have low B and N, you use 0.05. When you have high B and N, means the material will tend to what? Strain harden quicker, right? Logical mind say you should be what? Higher or lower? Can anyone answer the other? So if I will tell you, if I was to say that this is lower, can anyone tell me why? Hello? Anyone? No, because you know the right answer.
Well, so the elongation is it's softer, right?
No, with the high B and N, it's not softer. It's strain hardened more, right? It's strain hardened much more, so it becomes very. You look at the area under the stress strain curve, right? Right. The energy involved in machining B2 and N2 is much higher than B1 and N1. Yes or no? And the stresses are much higher, right? So in true mind, when you have something that has higher B and N, you should go lower. Okay, that is conventional way of thinking. Okay, what do I mean? We always think about anything into what we can relate with. Okay, so if you're going to bite something that is very tough, right? Will you take a bigger bite or will you take a smaller bite? Anyone? If you're biting something very tough, okay, are you going to take a bigger bite or a smaller bite? Anyone?
Smaller.
There you go. You will take a smaller bite. But because the other student made the right guess, okay, with the wrong reason, in fact, it should have gone the other way around. So this, you should be taking at 0.09 millimeters. Okay? And then cutter path planning, if it's low, is not critical. Okay? It's not critical. Hey, I don't know how to spell not anymore. Not critical. Okay, cutter path planning down here is very critical when it has high B and N. Okay, so what I'm going to do next is I'm going to explain why. Okay, I'm going to explain why when you have high B and N, right, you should take a higher undeformed chip thickness. And I have problem accepting the fact. Okay, when I was a young engineer, when I was working with Rolls-Royce, I have a fact. I have the fact of accepting the reason why when we have high B and N, I should take a deeper cut until I sit down and I start analyzing what is going on. Okay, so I'm going to draw to you, okay, to see why this is the case. Why, when you have low B and N, you take 0.05. When you have high B and N, you have to take a what? A much deeper or much higher undeformed chip thickness. Okay, so now we have a workpiece material. Okay, so this is our workpiece material. So this is the size. Okay, I will say again, this is the size that we buy. Okay, that we purchase from as a raw material. Okay, so over here I'm going to draw another line. Okay, I'm going to draw another line. So over here, this is our desired geometry. Okay, that is our desired. Oh, this is very bad. This is our desired geometry. Right? So whatever that's on top, okay, whatever is down here is unwanted. Right? So when we start machining this, right, we maybe cannot take a single cut. We possibly have to take 2 cuts. Okay, so this is our tool. All right, so this is cut number 1. Okay, so cut number 1. Okay, so this is our tool. And then after that, we follow by the next tool, or the same tool, but now it will go in to do cut number 2. Okay, cut number 2. And now the question comes is this, okay? So this one I call T1. Okay, this one I will call T2. Okay, usually, okay, so this is our workpiece material. Right? If the material has high B and N, okay, or low B and N, T1 is never the problem. Okay, it's usually T2 is having the problem. Okay, so this workpiece material has its bulk, okay, has its bulk hardness. So bulk hardness is whatever hardness it comes after you buy from the supplier. Okay, so we start machining cut number 1. Okay, so I'm going to draw cut number 1. Okay, so this is our workpiece. I'm going to shift it slightly. So this is our workpiece, or this is our tool. All right, so we get our chip. Right, so this is still going through cut number 1. Okay, we have not gone through, so cut number 2 we have not started yet. Okay, we have not started at cut number 2. Then so we know this surface, right? We know this surface over here is known as our newly generated surface. Okay, and all this over here, whatever is over here, all these are unwanted. Right, so we have not done cut number 2 yet. Okay, so all these are our unwanted. Okay, we have not done cut number 2 yet. Okay, right, so what happened is when we will measure hardness. Okay, we'll measure hardness. So every point I draw over here is a hardness measurement. Okay, so we measure the hardness. So this is hardness measurement location. Hey, today got spelling issue. Location. Okay, so when we measure Okay, this is the outcome. This is the results. Okay, so over here, this axis is our hardness. Okay. So this axis over here is what we call